Alrighty, this video is going to be about inclined planes. Inclined planes are considered a difficult topic, and I'm going to help you navigate through two things that normally bite a student when they're doing inclined planes. First, let's draw a non-inclined plane, a flat plane with a sizable object on it. Let's put a box, a 5 kilogram box, and no one's pushing this box left or right, but there are still some forces on it, and it's not accelerating, it's in equilibrium. So a free body diagram for this box would be a dot for the box. We would show the normal force from the surface going upwards and the weight going downwards. Now weight equals m times g. The mass is 5, g is about 10, so this is approximately 50 newtons. And we can infer that this must be 50 newtons. And this box is in equilibrium. But when we tilt the plane, some interesting things happen. So here's the original plane, and now we tilt it about 25 degrees or so, just to be concrete. 5 kilogram box. Now a free body diagram for this guy looks a little different. The dot for the box is the same and the weight is the same, but the normal force is now perpendicular, not straight up this way, but perpendicular to the plane. So we're going to need to componentize. And if we componentize with the standard coordinate system where y is up and down and x is side to side, then there's going to be two components of the normal. One component is going to be straight up along the vertical, right next to the angle that we know, and that's going to be n cos 25 degrees. Another component is going to be in the x direction, and that's opposite the angle. You could draw it over here or down here, your choice, and that's going to be n sine 25 degrees. So we would conclude that n cosine 25 degrees might be equal to 50, but you know, in this case, the box is not going to be able to hold still. There's absolutely no way for these two forces to be in equilibrium because there's this one force that is unbalanced. That means that this thing will accelerate. And the weird thing about this is the direction of the acceleration will be down the plane. That means the direction of the force is down the plane. So the direction of the force is some combination of this little orphan here that's by itself and weight. In other words, we cannot conclude that n cosine 25 is equal to 50 newtons. This is a real problem, and it could give you a headache if you weren't clever. But you are clever, and you have me to guide you. Let's draw that free body diagram again, but now let's choose a different coordinate system. Let's choose a coordinate system that has been tilted along with the plane. In other words, on this diagram, x was horizontal and y was vertical. What if we made x along the plane and y perpendicular to the plane? Then our free body diagram gets superimposed over this coordinate system. You could even call this the perpendicular axis, and you could call this one the parallel axis if you want to do so. Or you could just call them x and y and realize that they have been tilted. In fact, it is worth writing down that the secret to these problems is to tilt the coordinate system. That is important. By tilting the coordinate system, not only is the motion going to be in one of our coordinate directions, meaning we can kind of treat this like projectile motion, where there's something going on in one dimension and nothing going on in the other. But we don't have any more componentization to do. It's only weight that needs to be componentized instead of the normal. So weight will be componentized into two pieces, and one of them goes down this way and is the adjacent side. So it is w cosine of theta, and one of them will go down this way, and it is the opposite side, and so it will be w sine theta. And in this case, we can conclude that there is no acceleration in our new y direction, so we can conclude that w cos theta equals the normal force. Or if you want to write out what w is, mg cos theta equals the normal force. Now, mg was the old normal force. Now we multiply cos theta, which is something less than 1, so the normal force actually is a little less on an inclined plane. And then the other conclusion we can make is that this w sine theta is going to produce it's going to be our net force in the y direction, or x direction, excuse me, and it's going to produce our acceleration. So mg sine theta equals m times a. And since this m for the weight term and this m for the inertia in Newton's second law are the same, we can conclude that the acceleration down the plane will be g sine theta. And this is a general result. And you've seen that the role of sine and cosine have kind of switched. Cosine is being used for what was the y direction, and sine is being used for the x direction because of where the angle is. Now, learning that that angle is in here is something that is a personal journey. You have to do it for yourself. You can do it with geometry. You can do it by imagining. I will go up here and give you a little thing that can help you imagine where this angle is. We can go from flat to slightly tilted to seriously tilted to, oh my God, almost devastatingly tilted. And if we do so, we see in the flat that these two are opposite each other, and the normal force moves a little away from weight in this case, and a lot away from weight in this case, and as they used to say, hella away from weight in this case. And since the normal direction is the perpendicular direction, our y-axis will always be opposite the normal, always be opposite perpendicular. So for a large angle of inclination, this is a large separation. For a medium angle of inclination, this is a medium separation. And for a small angle of inclination, this is a small separation. So the angle is always between the negative y-axis and weight. All right, that should get you started with inclined planes. You tilt the coordinate system, you componentize the weight into two pieces. Normal will always balance out the piece that is perpendicular, and the remaining piece that is parallel to the plane is what causes your acceleration. This is the reason why Galileo used inclined planes to study gravity. He could dilute gravity on an inclined plane. There were no timing devices good enough for him to drop balls and time them with any degree of accuracy. But if you made them roll down planes, he got a dilution of gravity. The acceleration was much less, thus the problem took longer, and the timing elements that he used, whether it be his pulse or a pendulum or something like that, would be appropriate for this. Anyway, that's a short little lesson for today, and I'll put this online as soon as I can.